Right, grade 11, starting off today's session, following on, still with the intermolecular forces, but we're carrying on from last week. We ended off with polarization, and dipole to induced dipole force, or forces. And now we are busy with London forces, okay? Now, first of all, something we must know about London forces, it is the weakest, all right? The weakest, let me see, how should I call it? The weakest of all, that's better to say, van der Waals forces. It's the weakest one. They are quite easily overcome, okay? And London forces basically are also known as, aka, instantaneous. Instantaneous. Sometimes the word is a little. There we go. I can spell it. Right. I can still spell. I'm glad. Instantaneous dipole to induced dipole forces. Okay. So we obviously still understand induced dipole forces. Okay. But as I mentioned, it is the weakest, and these forces, they take place between non-polar molecules. Okay, non-polar molecules. So two non-polar molecules basically coming together. Okay, so what we need to just remember is that electrons in atoms or molecules, they are not fixed in space, but they are in a state of constant motion. So they're not standing still, they're not static, right, or statically put. See? Okay. When two non-polar molecules approach each other or collide for an instant, the negative electrons in the space around the nucleus, they will repel each other. Okay, let's maybe take that down a little bit in detail. Okay, or let me maybe just explain it, draw it, and then put some notes down. Okay, the negative charge around the nucleus becomes unsymmetrical. Up until now, before the collision, it's been symmetrical. As a result, the dipoles are formed for a brief moment. So, let's use the color green here. No, that's not green. That is dark gray. There we go. So, for example, if I got two non-polar molecules, and I'll draw them the same color. Okay, there we go. They're my non-polar molecules. Okay, and they approach each other. Okay, so up here, non-polar, and they're going towards each other. Okay, and I have two of them. Okay, as a result, this is what will happen. Okay, they will obviously collide and touch each other. Okay, but let me just make my pen a bit smaller. Two momentary dipoles will be formed. Okay, so you'll have a positive and negative. All right, and here will be your positive, here will be your negative. Okay, the same way. Basically, you see this is two induced dipoles now together, so we call them two momentarily. In other words, they don't last very long. Momentary, the Y should have been here, so let me just try and extend that R there. Momentary dipoles. Okay, so now what happens? Okay, they approach each other and they collide for an instant. The negative electrons in the space around the nucleus, they will repel each other, and the negative charge around the nucleus will thus become unsymmetrical. As a result, dipoles are formed, and they formed for a brief moment. They don't last very long. The opposite charges of the two momentary dipoles will give rise to a very weak intermolecular force. All right? So it's a very weak intermolecular force, and it's known as London forces. Okay, let's just put that down. Intermolecular force. All right. Now, the more electrons a molecule contains, the more readily momentary polarization occurs. To the strength of so the strength of London forces increases with molecular size. Okay? Let's add that down, that the strength of, and I'm going to use LF, London forces, increases as the molecule increases, or as the molecule size increases. So with molecular size. One of these key things with London forces to remember and to separate them in your mind from all the other forces that you have learned is that when these instantaneous dipole to induced dipole forces are formed, right, they do not last very long. They are but for a moment. Okay. If London forces increase with molecular size, this also results in boiling points increasing. All right. Now, what we must understand is, let's take an example such as iodine. Okay. But before we get there, let me just check. Do we all have this slide down? Can I change the slide before I take the example of iodine? Yes or no?
Yes.
All right. Wonderful. Okay. Let's take the example of iodine. I2. Now, the iodine or I2 molecule contains 106 electrons. Okay, make my pen a little bigger. Not that big. There we go. 106 electrons. All right. Now, the intermolecular forces between iodine or I2 molecules are strong enough. Okay. They are strong enough to be solid at room temperature. At room temperature, the intermolecular forces of iodine, they are strong enough to be solid. All right? But London forces are the only kind of intermolecular forces that exist between the atoms of noble gases. All right? They are the only kind of intermolecular force, all right, which exist between atoms in noble gases. All right? This is why these gases liquefy at low temperatures. Okay, so if we take noble gases, okay, and I'm sure we know that list. Noble gases, all right, they have London forces that exist between them. All right, London forces, and they exist in noble gases, and they will only liquefy, and keep in mind, I only knew how to spell this word like very, very recently, like a couple months ago. Liquefy at extremely low temperatures. Only at extremely low temperatures will London forces between noble gases or these noble gases turn liquid. Right? Otherwise, they will remain gas. Okay? The boiling points increase with the increasing amounts of electrons. All right. Now, going back to iodine, all right, which is I2, it has 106 electrons. That's quite a bit of electrons. And the London forces that exist between it, all right, keep iodine a solid at room temperature. Now, room temperature is not exactly very, very cool. All right, it's fairly warm for substances. All right, it's fairly warm, fairly. Okay, about 22 point. I think it's about 20. No. Am I getting this wrong? I think it might be around the 22, 24 degree mark Celsius. I think room temperature. If I'm correct, one of the students is welcome to go and get me an accurate answer if they so choose. The actual degrees Celsius of room temperature. Okay, but it's not exactly cool. And for that, for a substance to remain solid there means its intermolecular forces must be strong due to the fact that it has a lot of electrons. All right, and iodine has 106 of them. All right, which is quite a lot. Okay, and that means that the boiling point, all right, the boiling point also of iodine means it's going to be quite high. Right, because it has so many electrons, it's quite a big molecule, therefore more energy is needed to overcome it. But because London forces are weak, they are relatively broken quite easily. Okay, so this is the weakest of van der Waals forces. But what we're going to get to next is the strongest force which exists, or the strongest intermolecular force which does exist, right? And that is known as hydrogen bonding. Hydrogen bonding. Okay, I mentioned earlier, or when I say earlier, I mean in probably last week, that it is the strongest, one of the strongest intermolecular force, if not argued the strongest intermolecular force that does exist. And basically, when hydrogen bonds with small atoms of high electron negativity. Okay, so that's a very, let's just break down that statement. Okay, if an atom has a high electron negativity and hydrogen bonds with it, so let's take, for example, hydrogen, H2, plus oxygen. Okay, you get H2O, just water. So when hydrogen bonds with small atoms of high electron negativity, such as oxygen, okay, and other examples, or other atoms, also include the following, such as, let me use a colon rather, nitrogen, as well as fluorine. There we go, that's how you spell it, fluorine. Okay, then we have a situation where strong polar bonds are formed. Very strong polar bonds. Okay. Since the hydrogen atom has no inner shell of electrons, now that makes sense. Why? Because it only has one valence. It's in group 1, it only has one. It has no inner shell of electrons. Okay. The nucleus of the hydrogen atom is left exposed to these bonds. Okay. So that's just a note. There are no other electrons, okay, in the inner shell of hydrogen. It only has one to give, one to share. The nucleus is open to it. The positive hydrogen nucleus is easily attracted to a lone pair on a neighboring atom. Okay, it leaves the nucleus exposed. So hydrogen nucleus of its atom is exposed. What does that mean? It is quite easily attracted, right, to neighboring atoms. Okay, and that attractive force is called hydrogen bonds, or hydrogen bond. Okay, there are two conditions for hydrogen bond to form. Okay, two conditions. I'll write it a different color, and I may have to skip a line, or may have to go to the next page, or maybe write it underneath here. I'm not sure. We'll see. So the first condition, number 1. Okay, first condition number 1 is the hydrogen atom. We'll write it a little bit further up here. Okay, must be covalently bonded to a small atom which has a high electron negativity, which is what I said earlier at the beginning of hydrogen bonding, that hydrogen bonds to atoms, small atoms though, of high electron negativity, such as your oxygen, which we see here, we see hydrogen here, and we see fluorine here. Okay, that hydrogen atom must be covalently bonded to any one of those. Okay, and I have to unfortunately go underneath our little banner here, But the second one condition is that there must be a lone pair of electrons. There must be a lone pair of electrons on a neighboring pair or on a neighboring high electron negativity atom. I know Mary could spell it without a U, but yeah, I'm going to use the U here. On a neighboring, I need some more space here, I think. There we go. High electron negativity atom. Okay, those are the two conditions for a hydrogen bond to form. Okay, and this is asked and tested in the exam and tests, so please do not forget them. Okay, you can obviously shorten them to remember, but you need to write them out in full. First condition, must be covalently bonded to a small atom of a high electron negativity, and there must be a lone pair on a neighboring high electron negativity atom. In oxygen and nitrogen and fluorine, there are lone pairs. For example, nitrogen only has one lone pair of electrons. Oxygen has two. All right. You must check the periodic table to find out how many lone pairs fluorine has. I think it may also have either 2 or 3, or maybe also just 1. Okay. And then a hydrogen bond can be formed. So hydrogen bonds is not just, therefore, whatever hydrogen is bonded to. Just now you see it's got hydrogen in it. Oh no, it's hydrogen bonds. No. You need to check. Does the conditions satisfy your judgment of what a hydrogen bond is? Alright? Firstly, is it covalently bond? Does it have a high electron negativity? Secondly, is there a lone pair? The first condition may be right, but if it doesn't fit the second one, it's not a hydrogen bond. Could be a London force or any other van der Waals forces. So, because of hydrogen bonding or hydrogen bonds, because of the stronger intermolecular forces that exist in those molecules containing hydrogen to fluorine or hydrogen to oxygen or hydrogen to nitrogen bonds, because they are stronger, thus there are higher melting points as well as higher boiling points, but especially boiling. Okay. Ammonia, which is NH3H2O, and hydrogen fluoride should have the lowest boiling points, okay, but because of the hydrogen bonding, their boiling points are unusually high. And let's go demonstrate it quickly. So if we have a look at group 5, okay, group 5, some of those elements of the periodic table hydrogen can bond to on group 5, okay. So if we have a molecule such as NH3 up here, and then we have another molecule at the bottom here called PH3, and some other molecules like ASH3 and SBH3, okay, and if we have our little graph here, or temperature, here will be around about it will be about minus 100, like minus 75 over here. It's all degrees Celsius, and about here, around about just underneath here, we'd have about minus 50 degrees Celsius. Okay, you can see how high up NH3 is. Alright, and how low pH3 is, and then just plotting this graph here, you can see exactly where all these little points are. Alright, now according to this little drawing here, ammonia should actually have the lowest, but because of hydrogen bonding, it actually has one of the highest boiling points as compared to any of these. Even though it's minus degrees or minus 50 degrees Celsius, minus 50 degrees Celsius is a higher number than minus 100 in negative numbers. Okay, I'm sure we all understand that when it comes to maths. Okay, the -1, all right, the closer the negative number is to 0, the bigger it is. Okay, the further away from 0 we go to the left, the smaller the number gets. All right, I'm sure we understand that. I don't need to explain that. Okay, there are more obviously that exists. So if water is oxygen, which is in group 6. Right, water has the highest boiling point there of 100 degrees Celsius. All right, and if we go into group 7, all right, which is very similar to this, we see hydrogen fluoride has a boiling point of 0 degrees Celsius. All right, but chlorine, or not chlorine, but hydrochloric acid only boils at -100 degrees Celsius. All right, so those are those boiling points there. Okay, so that's boiling points when it comes to hydrogen bonds. Quite high. They take long to boil, especially with ammonia, water, and HF. They take long to boil because they have such high boiling points. Okay, so that's why water takes a while to boil, because it has to hit 100 degrees, right? And it's the highest. So hydrogen sulfide, H2S, that boils roughly close to -50 degrees Celsius after 0. So water, ammonia, and hydrogen fluoride should have actually the lowest boiling points, but because they have hydrogen bonding in them, or hydrogen bonds, because of the lone pairs and because they're covalently bonded, they take a while to boil. Alright, so what we do is we have a question here called question 2, and it's got some things of atomic combinations as well as intermolecular forces as well that I'll put into it. Alright, asking about covalent bonds and non-covalent. Alright, and then we got question 3, which asks for boiling points and also has a look at some other substances, but we're not going to look at vapor pressure. I just want to see question 4. Question 4 looks like we're getting into some other stuff over here. Yeah, so not going to get it. We're going to stick with question 2 and question 3. And we can always take another paper and have a look, but we're going to try the 2017 November paper, and so let's just do what we see on the screen here. Let me just make it a bit smaller. There we go. So consider the following reactions. We're given 2, and define the term covalent bond, which I'm sure we all can do, and draw some Lewis structures, which I'm sure we all can do. At 2.3, not a trick question, but how many lone pairs are on the central atom in CO2? Alright, molecule. Now take note, on the central atom. Okay, you need to tell me and know which atom is in the middle. Identify one of the substances in reaction 2, over here, that can form a dative covalent bond when reacting with an acid. Now, I think I did go through dative covalent bonds. Okay, but we can always look at that one a little bit later. And write down the shape of water and CO2. We can still remember that, I'm sure. At 2.6, although the molecules of CH4 and CH3Cl have the same shape, CH4 is nonpolar, while CH3Cl is polar. Give a reason for the difference. I'm sure we can do that one as well, since we know the difference between polar and nonpolar. Okay, so we'll take a few minutes for this. This one's about 11 marks, so I usually should give 11 minutes, but it's just gone slightly after 22 now, so I will mark just slightly after, or just before 5:2. We'll have a look at this question and mark it. Okay, take your time, it's fine, we're going to go through it. This is how we learn. Don't beat yourself if you don't know the answer just yet. Okay, work through it. Alright, so let's consider the following 2 reactions of methane. So in the first reaction, we should have seen that methane reacts firstly, methane gas with hydrochloric acid gas, HCl gas. And then the second reaction, methane gas also reacts with oxygen gas. Okay, 2 different reactions. Okay, define the term covalent bond. Okay, what is a covalent bond? Okay, well, we can easily do that. Okay, first of all, before we start answering the question, for the purpose of everybody watching, this is grade 11, and we're doing paper 1. Sorry, not paper 1. Oh my word, it's horrendous. Paper 2, November 2017. Okay. The question we were doing was question 2. 2.1. Define the term covalent bond. Well, a covalent bond, let me type in the word bond there, or write the word bond there. Bond is the sharing of electrons between two atoms, okay, to form a molecule. Okay, that's in a nutshell what a covalent bond is. Okay, there are other ways that we can obviously put that. I'm just going to get the second definition quickly. We obviously know what a polar bond is. We know what's polar, non-polar, all the kind of stuff. We obviously know about that. We obviously know what polar covalent bond means. I believe I did share dative covalent bonding when I was sharing Lewis structures. But a covalent bond, okay, another way to put that is the electrostatic attractive force between the electrons and the nuclei that keeps them held tightly together. That is also called a covalent bond. But the definition on the screen is worthy enough of achieving 2 marks. Okay, the sharing of electrons between two atoms to form a molecule. 2.2, I think asked you required you to draw some drawings. I think the first one was for CH3Cl. Okay, now you're going to have to pay attention to this one. Okay, well, what I like to do is write down all the atoms that I have in the molecule. Okay, I have 1, I've got 3 hydrogens and 1 Cl. Okay, so it looks like if I write down carbon, 1, 2, 3, 4. Okay, carbon makes 4 bonds. There you go. It's got 4 electrons in the outer shell. Okay, I've got chlorine over here. Also shares 1. Okay, and then it has lone pairs. Okay, so I'm going to make chlorine. It's lone pairs. 3 lone pairs. Okay, and it shares 1 with carbon. Okay, that's sharing. Okay, they're sharing. Okay, and then I'm going to, so I've made carbon my dot, I've made chlorine my X, and with H hydrogen, I'm going to use an open circle. So open circle, and an open circle, and there's my hydrogens. Alright, and now I have drawn CH3CH3Cl. Alright, pretty basic. Okay, pretty rad. Okay, if your drawing looks somewhat like that, well done. Then CO2, I think, carbon dioxide. So of course, carbon in the middle. And we know that oxygen is going to be on either side. Okay, so they're going to share some bonds. So 2 of carbon's bonds over here are going to share. Okay, carbon is my oversized period, and oxygen is going to be my X. Right, they're going to share CO2, and now we have to draw in oxygen's lone pairs. Oxygen has 2 lone pairs, either one. If you forget to insert your lone pairs, you don't get the marks. Right? You don't get them at all. All right? You don't get them at all. Okay? So please do not forget your lone pairs. Pay attention to the group of your periodic table that you are taking your bonds from, or that you're taking your elements from. Pay attention to that, and always include the lone pairs. Okay, I think that was basic. Let's have a look at the next question. 2.3, how many lone pair electrons are on the central atom in the carbon dioxide molecule? So let's go back to our previous page and let's pull up carbon dioxide molecule. Tell me, people in the class, are there any lone pairs on the central atom in CO2? Can somebody please, with a good pair of eyes, tell me what is the central atom in carbon dioxide? Give me the name. Anybody? Central meaning the one in the middle. What is the name? Carbon dioxide. I'm watching the chat and I see no answers there. No one's microphone's going on. What is the central atom in carbon dioxide? What's in the middle? The Lewis diagram is right there. Thank you, Connor. Carbon. All right. Come on, guys. The central atom is in the middle. It's not a trick question. I'm not trying to trick you. I'm not asking a hectic question at all. Now we've got that out the way, we now know what is the central atom. The question is, how many lone pairs are on the central atom? Now can we answer that question? Do we see lone pairs on the central atom of carbon? Yes or no? If yes, how many? If no, that's a final answer. Go. Thank you, Connor. Thank you, Kelly. No, there are no lone pairs. So what's our answer? 0 or none. Done. That's our answer. 1 mark. We walk away smiling. Money in the bag. Okay? I used to think of my marks as money in the bag. Cool. I just got 1. 1 money in the bag. Cool. No lone pairs on the central atom. Had there been a question, how many lone pairs in total on the oxygen atoms? Well, there are 2 lone pairs on either oxygen atom, so meaning 4. 1, 2, 3, 4. We can count, we can see it there. Cool. Now we've got that question out the way. We don't need to write that down. We can just go all the way up here. Okay. 2.4, identify one of the substances in reaction 2 that can form a dative covalent bond when reacting with an acid. Hydrochloric or HCl is hydrochloric acid. That's an acid. Okay. And they want to know a dative covalent bond with anything in reaction 2 that can form a dative covalent bond when reacted with an acid. Okay. Any takers on that one? Any takers? Okay. I know we haven't learned acid-base reactions just yet. All right. That's coming up soon. Okay. I have explained what a dative covalent bond is. Okay, they're basically atoms with an incomplete complement of electrons in their valence shells that can share lone pair if electrons from another atom or of electrons from another atom to form a dative or coordinate covalent bond. Okay, if we look at reaction 2, we have CH4, we have oxygen, and we have carbon dioxide, and we have water. Okay, so which substance there can form a dative covalent bond if it reacts with the acid? Okay, I'm leaving this question open for about a couple of seconds. If anybody would like to take a guess. A guess means you don't know, so you can just blurt things out. Okay, nobody? Okay, the answer there is water. H2O. Okay, water, if it reacts with an acid, forms a dative covalent bond. Okay, I'll show you quickly a rough little equation here. If you take water, you react it with any acid, basically the dative covalent bond that will form is a hydronium, H3O plus, all right, molecule that, ion that forms, and basically there's a shared lone pair that happens, all right, a shared lone pair that happens with H3O. Basically, we know water exists like this. Okay, but unfortunately I have to do the Lewis structure of it now. So if I have hydrogen here, and I have hydrogen at the bottom here, so you got your lone pair there of of oxygen. You got your hydrogen, oxygen molecule, hydrogen, oxygen molecule, and then you got lone pair of oxygen also there, because oxygen has two lone pairs. Basically, hydrogen rocks up here and decides, hey, I'm going to share a lone pair with you. That's why I get H3O plus. Okay, and this would be an example of a dative covalent bond. Okay, this we'll learn more under the section of acids and bases. So therefore, that answer was H2O for question 2.4. We haven't got to acids and bases just yet. Okay, 2.5. I think they asked us to write down the shape of the H2O molecule. Shape of H2O molecule, please. Anybody? Somebody?
Bento-angular.
Bento-angular. Okay, can somebody please give you the shape of, I think it's 2.5.2, of CO2, carbon dioxide? Connor, you are correct. Anyone else said that as well? It is linear. Right? It's linear. Okay? It's in a straight line. Okay? Also, if you didn't know that, you could have just looked at the Lewis diagram that you drew, and then it'll tell you that it is linear. Okay. Last question. Let's have a look at 2.6 and what the question was. It says, although that the molecules of CH4 and CH3, they have the same shape. CH4 is nonpolar, while CH3, Cl, is polar. Just give a reason for the molecular polarity. Okay? Now, when we spoke about VSEPR shape, or VSEPR theory, we looked at the shape of molecules, we noticed that there was words such as symmetrical and asymmetrical. Alright? So a reason for why they have the same shape, but the one is polar and the one is non-polar, one of those reasons is that the charged distribution in CH3Cl is asymmetrical. Alright, and CH4 is symmetrical. Okay, in just the way the charge distribution is. But another reason, and the reason that I like, okay, so I'm going to go or here, is that the chlorine, or the Cl, alright, has a higher electron negativity, okay, than hydrogen. Okay, so if you have a look there, all right, Cl has a high electron negativity than the hydrogen in CH3Cl. That's why the molecule is rendered non-polar, while in CH4 the molecule is rendered polar. Okay, also because of its symmetry, the molecule is very symmetrical, almost like it could fold very easily if it were paper. Very symmetrical, axis of symmetry. Okay. That wraps up this question of this paper. See if we can do another one. Alright, so here we got grade 11 November 2015. Alright, November 2015. And pretty much similar to November 2017. This is just to consolidate what we've learned. And what I like about this is that this is a question of a solution I've already shared like about 5 minutes ago. So this is about 17 marks. Okay, so we're just going to go as quick as we can It's 1/4 now on my watch, so we can go until about 20 past. So I'm only going to give certain questions. So please make sure that you take note about the questions I'm about to share. And I'm also going to write them down on my side so that I also don't forget. Please, can we do question? So we've already done 2.1 in another paper, in the 2017 paper. We defined them. What I want to do is, can we please do 2.2? 2.2. Can we please do 2.3? Okay, so that is 2 marks. 2.3 is 3 marks. That's 5 minutes. And then can we please do 2.4? That should take us to about just before 25 past. So 5 minutes, that's 8 minutes. Okay, it'll take us, actually take us to 25 past and 5 minutes to mark. So 2.2, 2.3, and 2.4, please. Thank you. Alright guys, we should be like low-key, almost finished. Right? Low-key. Alright, with everything, we should be possibly by now finishing up 2.4. Okay. Okay, so what we're going to do is, we're just going to mark it quickly. So let's just have a quick look at 2.2. It says one of the above molecules has lone pairs of electrons on the central atom. Draw a Lewis diagram for this molecule. That's pretty easy. So we know CO2 was the first one there. So it said molecules such as carbon dioxide and H2O are formed through covalent bonding. So then one of those has lone pairs. And we know for 2.2 that one pair is water. So we draw water. There we go. There we go. And then I'm making my hydrogen my dots, so then oxygen. Well, I'll make oxygen my dots. There you go. It doesn't really matter. And there's the Lewis structure for, sorry, let me do that. There's the Lewis structure for H2O. That was pretty basic. Okay, 2.2, 2 marks each. Okay, 2.3 I think was the next question. I said yes. H3O plus is formed when H2O forms a dative covalent bond with an H plus ion. Draw the Lewis diagram for H3O plus, which I did earlier on just before we ended off the previous paper, which was basically similar to the water molecule. Okay. There's this lone pair there, lone pair, and hydrogen over there, rocks up there. I just want to make sure something in my hydrogen there that I'm not leaving out a plus. I need to include a plus sign here as well to show that a hydrogen plus has now joined. Okay, and I'll just take the, you don't have to do what I'm doing here in orange, okay, of course, you don't have to do that. They know what you are writing down in any case. And now we're going to go 2.3.2. 2.3.2 says state 2 conditions, okay, for the formation, all right, of such a bond, okay, 2 conditions, okay, about the formations of such a dative covalent bond. Okay, that we will learn a bit closer when we get to acids and bases. Okay, so what I'm actually going to do is actually not even going to put that out, or I'm actually not even going to put myself out with that right now actually. So I'll actually save that for when we do acids and bases a little bit later on in the year. Okay, so we'll leave 2.3.2 for now. We'll let that one go. I actually just realized, let me just leave that, let me just let that go. Okay. Let's rather move on to 2.4, which is the polarity of molecules depend on the difference in electron negativity and molecular shape. Define the term electron negativity. Okay. Electron negativity. Now, there's many ways that we can define it. Okay. I'm just going to rather use the way that obviously I know best. to ensure that we get the marks. So 2.4.1. Okay, taken straight from the definition that we looked at a couple weeks ago, is that the electronegativity, all right, is basically the strength of an element's ability to attract electrons, right? So the strength of an element's ability to attract electrons. Okay, that's what electronegativity is all about. And I think in 2.4.2, okay, there were two calculate the electronegativity between carbon and oxygen in CO2. Okay, so we'll do that first. We know that the change in electronegativity strength is equal to the electronegativity of A minus B. Okay, so we got CO2. So I need a periodic table. Periodic table can help. Let me just get a periodic table open here quickly so I can see the electronegativities of either or. There we go. So I've got electronegativity, that's a carbon to oxygen bond. Alright, let me just see. So I've got oxygen there to be 3.5. So I've got 3.5 for oxygen minus 2.5 for carbon. And that should give us an electronegativity of 1. Alright, that should just give us an electronegativity of 1. And then I think they wanted the electronegativities of H and O. So this is 2.4.2. So that's B. This was A. And let's have a look at B over here. Change in electronegativity equals 2. Oxygen was 3.5 and hydrogen was 2.1. So 3.5 minus 2.1. And it's about 1.4. Right, it's just a number. It's 1.4. And that's where we are going to call it a day there, grade 11s.